Good morning. I'm Kiran, student of Basic Chemistry Honors final year. Unit is Thermodynamics and Kinetic Aspects of Metal Complexes. The formation of metal complexes in aqueous solution is a matter of great importance, especially in inorganic chemistry. Invariably, all metal ion in aqueous solution exist as MH2NX, where N is coordination number while X positive is oxidation state of metal. The interaction between a hydrated metal ion and a reagent in forming a coordination complex is regarded as a Lewis acid base reaction. The stability of the complex formed is related to thermodynamics and referred to tendency of formation of complex at equilibrium. It is appropriate to understand that stability of a complex compound refer above mean that the compound exists and can be stored for a long period of time under suitable conditions. Thus, the terms stable and unstable are thermodynamic terms representing the tendency of species to exist or not. The term stability referred in preceding paragraph gives a measure of final position attained in equilibrium measure but does not give any indication of the time taken to reach the equilibrium point. The term stability can also be used in terms of reaction rates. When reaction rates are considered, complexes can be classified into general types: labile and inert. Labile complexes react rapidly with inert complexes react much more slowly. Thermodynamic stability of complex ion. The thermodynamic stability of complex determines the extent of formation of complex at equilibrium. The stability of complex depends upon strength of bond formed between central metal ion and reagent. If bond formed is strong, the complex found would be thermodynamically more stable. Thermodynamically stability can be expressed in terms of equilibrium constant for formation of complex. When ammonia is added to aqueous solution of copper 2 sulfate, there is noticeable change in color because the blue Cu2 positive ion are converted to deep blue tetraamine copper ion. The reaction takes place can be represented as Cu2 positive plus 4NH3 gives rise to CuNH3 whole twice 4 2 positive. High value K would mean that ion is thermodynamically stable. The equilibrium will be lie to right. Thus, the equilibrium constant K refers to the stability constant of the complex. The higher the value of K, greater is stability of complex. Alternately, 1 upon K value sometimes. Thus, the log Bn is generally used as a measure of stability of the complex. The value of log B4 in case of this. A comparison of log beta value is amine complex of copper and candium indicate that complex is more stable than candium complex. This explains clearly as why Cu2 positive ion does not precipitate out as Cus when H2S gas passes through a solution containing CuNH342 positive complex, whereas CD2 positive readily form yellow precipitate of CDS when H2S gas is passed through a solution containing CdNH3 positive. The numerical value of stability constant describes the relative concentration of species at the equilibrium. The large value of stability constant indicates that the concentration of the complex is much greater than the concentration of the compound of which it made of. In other words, the complex is stable if equilibrium constant displaying its formation is large. A log K value greater than 8 suggests that the complex to be stable. Similarly, thorium can be determined in the presence of divalent cation using EDTA4 negative. The analysis of thorium is possible because of the large difference in formation constant for the EDTA4 negative complex of 4 positive and 2 positive cation, factor affecting the stability of the complex. Complex are found by the interaction between a metal ion and a reagent. The stability of the complex depends upon several factors, to which two are primarily important: nature of central metal ion, nature of legend. Let us first describe as how the central metal ion affects the stability of the complex. The stability of the complex depends further on size of central metal ion. Small size metal ion form stable complexes. The stability of the complex increases with decrease the ionic radii of central metal ion as charge density on central metal ion. Charge density means ratio of charge to radius of the ion. Charge density is higher in cases where the size of ion is small and carries high charge. It has been found that complexes formed by metal ion with high charge density are more stable. A smaller and highly charged ion can approach the legend more closely. As a result, there is greater attraction between the metal ion and the legend, which result in formation of stable complex. In brief, stability of complex increases with increase in charge on the central metal ion. This is evidenced by the fact that complex Fe3 positive ions are more stable than those Fe2 positive ions as the summarized. Complex with large overall stability constant are more stable. Electronegativity of the metal ion. Electronegativity of metal ion plays an important role in determining the stability of the complex. On the basis of electronegativity, metal ion can be classified broadly into two classes. This concept of classification of metal ion was introduced by Ehrland, Chet and Davis. Accordingly, class A metal includes the alkali and alkaline earth metal, first transition series and lanthanides and actinides. Class B metal includes heavy metal ions. These heavy metal ions contain large number of d electrons beyond an inert gas core. Similarly, other heavier electronegative metal ions such as Hg2 positive, Pb2 positive cation form insoluble sulfide salt. The formation of these stable salts indicates that these metals prefer sulfur-containing legend due to considerable covalent character in metal-sulfur bond. The nature of legend. The stability of the complex also depend upon nature of legend. Some of important factors associated with the legend are size and charge of legend. The size and charge of legend determine the stability of the complex. For example, the smaller F negative ion forms stable complex than the larger Cl negative ion as the evidenced by the stability constant of the complex formed. It means larger ion Br negative, I negative, ClO4 negative should be less stable. In fact, larger ions have little tendency to form stable complexes. Similarly, the small di-negative ion O2 negative ion prefer to form stable complexes with class A metal or electropositive metal. In brief, class A metal forms stable complex with strong electron donor. Basic character. The basicity of the legend play an important role. Greater the case is with which the legend donate electron pair, greater is the stability of the complex formed by it. Basicity of the legend determine how easily it can donate electron. A strong base is a good electron donor and many common legend like Cn negative, F negative, NH3 are strong base. In other words, greater the base strength of legend, greater will be the tendency to form stable complex. The base strength of molecule determines the stability of the complex that the molecule form with H positive ion. It means the legend which form H positive ion firmly should form stable complex with metal ion. There is something common in formation of acid and a complex ion as H positive plus base gives rise to acid M plus legend complex. Thus, F negative ion should form more stable complexes. Similarly, NH3 should be a better legend than H2O. This type of behavior is elegantly observed for class A metal that includes alkali metal, alkaline earth metal, first row transition metal lanthanides and actinides. However, it is not true for class B metal. Ion of more electronegative element class A metal attracts electron weakly and form more stable complexes with the legend containing NOF atom. On the other hand, class B metal ion forms stable complex with legend containing PSBr and iodine. Such legend containing PS, bromine and iodine atom are capable of accepting pi electron from the metal atom. In between these two classes, there are metal ions that possess intermediate character in forming complex. Such metal ions are preferred as the borderline metal. Common examples of borderline metals are MnW, Tl, Pb, etc. The bonding between a central metal ion and a ligand is due to donation of the electron by the ligand to the central metal ion. A strongly electron attracting metal ion is accepted to form stable complex. Electronegativity negative metals such as those of copper family, zinc family, together with Pd, Pt, Rh, Ir, Pb, etc. form stable complex through the covalent bonding. For example, silver form insoluble halides such as AgX and stable halide complexes AgX2 negative, in which the order of stability is I negative is greater than Br negative is greater than Cl negative and is greater than M negative. The value of log B of silver halide are this. This is all about thermodynamics, kinetics, except of metal complexes. Thank you.